Hello and welcome back to the Edge product line video series. My name is Charles Johnson and I am the lead trainer for Lynxspring. Today we're going to talk about setting up the inputs and outputs for our Edge device. We have done so far a commissioning of an Edge 534 and we then have ran the Onyx updates for that Edge 534. So now we are going to create a VAV air handler, and we're going to be setting up just the inputs and outputs today. The following video will probably be broken into multiple parts about setting up logic, because there's a lot of logic to go into a VAV air handler. So I've already expanded my station, and I've expanded my config space, and I've expanded my drivers to expose the Onyx network. When I double click on the Onyx network, I'm going to see my main Onyx device under the Onyx device driver device manager. The first thing that I like to do personally for me, and it's recommended by Lynxspring, to rename the Onyx device itself. And I'm going to name mine AHU_11. And the reason why I like to rename my Onyx device is that suppose that I have multiple pieces of equipment that I'm going to be controlling with an Edge 534 or another Edge product line with multiple XMIO boards. Each XMIO board probably will have a different piece of equipment, so I could be running an air handler on this one, maybe another air handler on the next one, and maybe even like a small hot water or chill water plant on the following one. So that way, at least for us, when a technician or another programmer were to come behind the job, they can actually see what device they're actually working on. Now, I'm going to expand my Onyx network, and I'm going to double click my points container. This brings up the Onyx driver point manager. Because I like to make sure things are more organized, I'm going to create a new points folder to discover my IO points. Now I can discover the IO points right now and just put them under the points container, and that'd be fine, and that could be your preference. For me, I just like things to be significantly more organized, and I have a specific structure in which I lay out my programming, whether it be for any JENEsys product or any other product in previous life that I have done. So I'm going to create a new folder, and remember, I'm not going to right-click on the points container and create a new folder. I'm going to, under the Onyx driver point manager, select new folder, and I'm going to name it hardware_IO. The reason why I'm creating a new points folder and not a new folder under the points container is because if I just do this, the default view is the wire sheet. But with the points folder, it is added the Onyx driver point manager as the default view, and therefore I can discover my points in this folder. So that's really the difference between the two. We'll be using a bunch of these for our logic, but as of right now, we're only focused on the hardware I/O. So make sure that you go to the hardware I/O folder and click Discover. Now, when I click Discover, this brings up 16 universal inputs, 10 Boolean outputs, 8 analog outputs, and 4 internal inputs. Well, but Charles, you said it had 34 points of I/O. Well, I did, and it does. So we can use 34 I/O points to wire up to. These 4 points are already built-in diagnostics for us to use and monitor. That way, you can check to see whether or not anything, if there are issues that are wrong, these 4 points can actually help you pinpoint that problem. When you add a point from the discovered pane to the database pane, you can do it in multiple ways. One, we can just click and drag, and it brings up the Add Points window. We can then double-click the point to bring it in here, or we can just highlight and click Add. Now, we can also multi-select and click Add, and it does the same thing here. Whatever your preference is to add points, please go ahead and use that. So I'm going to bring in my first point, and we see that there are a bunch of different input points here. So the first one that we see is the voltage input point, and basically it's just a numeric point that that reads a 0 to 10 VDC signal, an input signal, and produces either a voltage value or a linear scaled output value. The resistive input, again, is a numeric point, and it reads a resistive signal from 0 ohms to 100,000 or 100K ohm range, produces either an ohms value or, again, a linear scaled output value. If we do a thermistor input, it does the same thing. We can either read a temperature or some other scaled value if necessary. The counter input, the current input point, that reads a 4 to 20 milliamp signal and produces an amperage value. The counter input point is a numeric point that counts the number of contact closures at the input. So this is great for pulse counters. Then we have your Boolean input resistive, Boolean input voltage, and Boolean endpoint current. So these are all Boolean points that read either a voltage, a current, or resistive input, and it either creates an on-off status because of that. So for our first input, though, we're going to do a Boolean input resistive point, and we're going to name this fan status. And for my true text, I'm going to name it running. And my false text, I'm going to name stopped. Now, whether you want it to be start, stop, on, off, running, stop, again, that's really up to you and what your naming conventions are. I personally like running stopped for me, but that is, again, that would just be completely up to you. So now, because this is going to be a VAV air handler, obviously there's going to be an outside air, or at least we're going to have some kind of economizer, so therefore we kind of need a few more Boolean inputs first as safeties for this unit, and then we'll get into the analog inputs. So because the rest of these are all going to be inputs, or all going to be Boolean, these three, I'm going to multi-select them, and I'm going to bring them in. The first thing I want to make sure that I change them to is that they're all Boolean input resistive, and that their true text is going to be alarm, and their false text is going to be normal. Now, universal input 2 is going to be my free stat. Input 3 is going to be my smoke detector, smoke alarm, and my fourth input is going to be high static. Now I'm going to add my temperature inputs, 5, 6, 7, and 8. And again, I'm going to multi-select all of these, and I'm going to make them a thermistor input point. Now, because we're in the US, and unless you're really in a lab, most people are going to want degrees Fahrenheit rather than the metric system. So we're going to click OK there. Now, precision. Precision means this is the number of digits that are after a decimal point. If this were a space sensor, I would probably choose 0, but again, that's my personal preference. For any other temperature sensor, I will always do 1 as precision to read 1 point after the decimal. And now I'm going to name my points. supply temp sensor, my return temp, my outside air temp, actually mixed air temp, and my OA temp sensor. So I'll say SA temp. And then RA temp. And MA temp. And the only reason why I'm going back and changing them is because I have OA temp instead of just writing the whole thing out. Click OK there. Now, we definitely need a static pressure sensor. We're also going to add an outside air humidity in case we want to do potentially enthalpy control for our air handler, as well as a return air temp humidity sensor. I mean, a return air humidity sensor. So we're going to select the next three, and we're going to hit add. And now all of these are going to be voltage input points. Now, two of them are going to be humidity, and one of them is going to be pressure. So the first thing I want to do is I'm going to set up the first two. And I'm going to change the facets from voltage to percent humidity, which is under the miscellaneous tab. And I'm going to select 1 as the precision. And now I would like to do a conversion here. Now, to do a conversion, we need to figure out what kind we want. And typically, we're going to choose a linear conversion with a scale and offset. To determine the scale, we're going to take the output max and the output min, the difference between those, and divide that between the difference of the input max and the input min. So our output we want to be 0 to 100, and our input is going to be 0 to 10. So in this case here, it's going to be 100 divided by 10, which is going to give us 10. And then y1 is going to be 0. And we're going to subtract that from 10 times 0, which is going to be 0. And that's going to give us 0. So for a 0 to 10, which is 0 to 100, our scale will always be 10 with an offset of 0. And do 10 with an offset of 0. Now, input 9 is going to be OA humidity. I'm going to say OA RH underscore SNSR. RA RH SNSR. And now, this one here is going to be a 0 to 5 input. I mean, 0 to 10 volts equals 0 to 5 inches of water column. So we'll just name it right here, SA static, SNSR. The facets we're going to change from a voltage to a pressure, and we're going to select inches of water. We're going to do, we are going to keep it at 2 for our precision. And now our linear is going to be, our output max is going to be 5 minus our output min, which is going to be 0. And we divide that by 10 minus 0. So our scale is going to be 0.5. And now our offset is still 0, and our scale would be 0.5 times 0, which would still give us 0. So now this scale is going to be 0.5, and we're going to select OK. Now currently, they all show up as a fault right now, but we will fix that a little bit later on today. Now, we are going to go ahead and select our outputs that we have. So we have a Boolean output, which is going to be our supply fan. So we'll say fan command. Our true text, I want to be start, and our false text, I want to be stop. And now I have 4 analog outputs that I want to do. I want to do a fan speed. I would like for us to do a chill water valve. I'd like for us to do an economizer, so outside air and return. And then I want us to do a relief damper that will actually track the economizer dampers. So I'm going to select 4 outputs, and I all want them to be 2 to 10. So the first thing I do is after I add them all, let's go ahead and get them all set up as 0 to 100. Now when it comes to outputs, and especially percentage outputs, I always do the precision to 0. I don't really see the need to switch them separately. So to me, 0 to 100 is always good to see. All right, and they're all going to be 2 to 10, which means now that my output max is going to be 100, and our output min, our input max is 10, our input min is 2, so that's going to be 8, which is actually going to give us 12.5. And now our output min is 0, and so it's going to be 12.5 times 2, which is going to be our input min, which is going to be minus 25. So we're going to choose linear, and our scale is going to be 12.5. And our offset is going to be minus 25. And we're going to select OK. So now you're wondering why these went to fault when we've set them up properly. And the reason why they went to fault is that every point underneath has this linear calibration. Now, in the beginning, this is actually how you were able to set these up. They created their own linear calibration block. However, because now that we have created here in the proxy extension, we actually don't need to do this anymore, so we can actually delete these 3 linear calibration points, or calibration extensions. And now we go back to our hardware I/O, and we see that we have everything here. And of course, I did this a little too quickly, and I did not change the point names. So A01 is going to be fan speed. A02 is going to be my chill water valve. My A03 is going to be heating valve, or is going to be my economizer, so econ dampers. And then my A04 is going to be relief damper. Okay. So now I have all these set up the way I want, and we can continue on with the creating of the remaining logic in the next video. So I hope that you've enjoyed this, and I will see you next time.